And so our definition is all about the H+. You would have no HCl's. That's the definition of a strong acid. So most of them would be together and only a few hydrogens come off. First of all, what we need to do is get our definitions of acids and bases. So there are basically two definitions. And for an Arrhenius definition, which is an aqueous solution, acids are anything that increase the concentration of hydrogen ion. So remember, our little brackets means molarity. And then a base is anything that increases the concentration of hydroxide. So in a solution, that's what happens. Acids, H+, bases, hydroxide. But what if you're not in an aqueous solution? So we have this other definition, which is Bronsted-Lowry, I abbreviate BL, and it's very similar actually. An acid is anything that donates an H+. Okay, so in a reaction, if something provides an H+, it's an acid. And then a base is anything that accepts an H+. And so our definition is all about the H+. So in a reaction, I want you to look for H+, what's coming and going. So many acids, when you see a formula like this, you recognize hydrochloric, sulfuric, hydrofluoric. If you see an H on the front, most likely it's going to be an acid. So take a look at this reaction here. We're going to identify the acids and bases. So what you're going to look for is what happens to NH3. Here's the before, and then here is after the reaction. So what did it do? It gained an H+. So this is what we call the Bronsted-Lowry base, because he accepted an H+. Now, the acid here is water, because water starts off H2O, ends up with a hydroxide, so it donated an H+. So this is the Bronsted-Lowry acid. Now, what it becomes when it gives up its H+ is what we call a conjugate base. And then a conjugate acid is the base once it gains the H+. So these are acid-base pairs. All right, reactions. There are a couple that you need to be able to write for acids. What do they do in water? Well, it depends if it's strong or weak. And let me just say right here, strong acids do not mean super concentrated. There are some acids that are defined as strong and some are defined as weak. So what is the definition? It has to do with how much dissociates in water, or how many of those H+ actually come off of the acid in solution. So the definition, a strong acid completely dissociates. So hydrochloric acid is a strong acid. Every single one of those acids comes off. So in a solution, you would have only H+ and Cl minuses. You would have no HCl's. That's the definition of a strong acid. So a 0.1 molar concentrated solution would have none of those. It would be 0.1 molar concentrated in each of those ions. Now, the strong acids, the best thing to do is just memorize the strong ones. Here they are. And there's no trick to it, just memorize them. That way, any other acid that you see, you will know it is weak. So here they are, and notice they've all got a big H on the front. Okay, so no trick to it, just memorize the strong ones. Now, what does a weak acid do? Well, it only partially dissociates. So what we have is an equilibrium situation where it's going both directions. So some of the H+ come off. So in this one, we would have mostly acid together, okay, and then there would be a few hydrogen ions that came off. So most of them would be together and only a few hydrogens come off, okay? So the acid dissociation constant, hey, that is just an equilibrium constant that we write for this acid dissociation reaction. And so the Ka in this case would be the concentration of the hydrogen ion, and then whatever anion is left divided by the concentration of the acid as a whole. Okay, and those values are written in tables. You can look those up at various temperatures. And the larger the Ka, that means the more hydrogens come off. If you had a really tiny Ka, that would mean it's very, very weak. Very few hydrogen ions come off of that. So that is how you write the reaction for a weak acid.